Let's watch some crazy stuff, yo!
Welcome back to Pre-Calculus. In this video, we're going to continue section 10-8, polar graphs. And today we'll talk about some of the special ones. Several important types of graph have equations that are simpler in polar form than rectangular form. For example, a circle with a polar equation r equals 4 sine theta, that was example 1, has the more complicated rectangular equation, x squared plus y minus 2 quantity squared equals 4. Several types of graph have simpler polar equations shown below. So if we're in the form of a plus or minus b times cos theta, or plus or minus a plus or minus b sine theta, a and b are both positive. If a divided by b is less than 1, we get a limacon. It's got this little swirl that comes into the sort of circle shape. If a divided by b is 1, it's a cardioid, or a heart shape. You know, we got a little dent right there. If a divided by b is between 1 or 2, it's a dimpled limacon. So we just got that little dimple there. And then if a divided by b is greater than 2, it's a convex limacon. So it's almost a perfect circle shape. We've got rose curves. Here it's cos of n times theta, cos of n times theta. These ones are sine of n times theta. Well, if n is odd, you have n petals. Like this n is 3, we have 3 petals. N is 5, we have 5 petals. If n is an even number, we double that for the number of petals. If n is 4, we're going to have an 8-petaled rose. If n is 2, we're going to have a 4-petaled rose. And just by glancing at these, you can see there's a lot of symmetry in these graphs. Circles and lemniscates, you know, here's our a cos theta, a sine theta, are circles on the x and y axis. And then here, r squared equals, r squared equals. We get sort of this figure 8 shape that goes through the origin. All right, the quick test for symmetry presented can be used, especially useful when graphing many of the curves shown, blah, 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 blah. First, let's do a review of, let's hit the tests for symmetry. So if we want to check for polar axis symmetry, also known as the x-axis, I'm going to write it down here. The test that we perform is we replace theta with negative theta and see if it simplifies back to the original form. So let's look here at our x and y axis. This point here would be r comma theta. Here's our angle theta. And if we make angle negative theta, it means we're going to come down here, negative theta, and this point would be r comma theta. This is our x-axis. Notice these points would have the same x-coordinate. If we go straight down, the x-coordinate is the same, so we have x-axis symmetry. So again, we're going to replace theta with negative theta and see if it simplifies back. That is our polar axis symmetry. We can also check for theta equals pi over 2. That's the y-axis. We can check for that symmetry. So the test for this, we're going to take out theta, and we're going to replace it with pi minus theta. And up here on the axes, let's see, so this would be our angle theta. And we want to be symmetric around the y-axis. So that means we're going to wind up over here at the same y value. Now, back when we did what do they call that? Dang it, it's slipping my mind. The other angle here, reference angle. This angle theta in red would be the same as black. So this angle I'm tracing in blue, that would be pi, half of a circle, minus whatever theta is. So again, we replace theta with pi minus theta and see if we get back to where we started. And the last type of symmetry is pole symmetry, or the origin symmetry. So on this one, let's say here we've got this angle is theta, If we're symmetric around the origin, that means we'll be shot across the origin to the other side. So I would take angle theta, and here's half a circle. In radians, that's pi. So our test for pole symmetry, we're going to replace theta with pi plus theta. All right, so there's our 3 tests to see if we have these types of symmetry. So let's check example 5. I believe in the notes I gave you, we should have one more box on here with pi 2. Pi over 2. So the type of curve here, we know it's going to be a rose curve. And this is an even number 2, so we're going to have twice as many. We're going to have 4 petals. Now we're going to check each of our types of symmetry. Our function r equals 3 cos 2 theta. And, let me back up here real quick. Cos, I did mention this a long time ago in class. You've probably forgotten. The cos of theta is exactly the same as the cos of negative theta. If we think about on the unit circle, let's do pi over 4. At pi over 4, your cos value is root 2 over 2. If we go down into the 4th quadrant, negative pi over 4, your cos value, your x-coordinate, is also positive root 2 over 2. So when we're looking at cos, what I've said in class before is cosine is hungry and it eats negatives. So here's cos, it's hungry. This negative in here is just going to come out and cosine's going to eat it and it's gone. So cos of theta and cos of negative theta are equivalent. With sine, that's not the case. Sine of theta, let me back that up. Sine of negative theta is like the negative sine of positive theta. So sine is not hungry. This negative escapes and just jumps out front. So the sine of negative theta is the negative of sine theta. This will help with our simplifications today. So we've got r equals 3 cos 2 theta. We are going to test for polar axis symmetry. Polar axis symmetry. So we're going to replace this theta with a negative theta. So that's going to hit that 2 and become negative 2 theta. Now I just said cosine is hungry, cosine eats negatives. So this negative is going to get eaten up, it's gone, and we're back to where we originally started. So we do have polar axis symmetry. All right, let's check now for pi over 2, or y-axis symmetry. So we're going to replace theta with pi minus theta. So this is going to be 3 times the cos of 2 times quantity, pi minus theta. All right, well, my algebra in me tells me to distribute the 2. So now that's 3 cos of 2 pi minus 2 theta. And just because I feel like it, let's reverse those orders. Let's put the negative 2 theta first, and then the 2 pi will be a plus 2 pi. Now think back when we were learning about the unit circle. 1 trip around the unit circle is 2 pi radians. So this plus 2 pi means we're just going to do another lap and end up right where we were. So we can ignore the 2 pi. Now here we've got a cos of a negative 2 theta, and once again cosine is even, it's hungry, it's going to eat that negative up, so it's gone. And now we are back to where we originally started. So we also have pi over 2 symmetry. Okay, and for the last one, we're going to check pole symmetry or origin symmetry. That means we're going to replace the theta with pi plus theta. Pi plus theta. Once again, distribute the 2. So now we've got 2 pi plus 2 theta. And we could write it in reverse order, but once again, 2 pi is just another trip around. We can ignore it. So we're back to 3 cos of 2 theta, right where we started. So we also have pole symmetry. We have all the symmetries available. All right, and to save a little time, let's not find the max value in the zeros. That will show up as we do the graph. All right, so in class, we would get out our TI-89 calculators, and we would start plugging in some values. So 0 goes in, 3 comes out. Pi over 6 goes in, we get 1.5. Pi over 4 goes in, we get a 0. Pi over 3, our output is negative 1.5. And then finally, for pi over 2, we get negative 3. So there's our points. It's not many for a 4-petaled rose, but we have 3 types of symmetry to aid us. So here's the graph. Let me make this a little bit bigger. All right. Remember, x-axis, y-axis, and origin symmetry. So we're going to start at 0, 3. So on the 0 radians, we're going to go out 1, 2, 3 units. We're right on the x-axis. So this is reflected to itself over the x-axis. But we do have y-axis symmetry, so I'm going to hop across the y-axis to that same point away from the origin, and that would be this point right here. So there's our y-axis symmetry, and this is also the origin symmetry, because here's the origin. We went through the origin, the same distance on the other side. So there's our second point there. There we go. I'm going to switch to blue ink. Pi over 6, 1.5. Well, here's pi 6. I'm going to go out from the origin, 1.5. So this is my original point. Now let's do x-axis symmetry. That means we'll go straight down onto the 11 pi 6 ray at the same point. Back to the original. We're going to cross over the y-axis. That's going to put us on the 5, 6 pi ray right here. And if we go back to the original point, if we cross the origin, we'll have our final point. So this pi over 6, 1.5, gave us 3 additional points from the symmetry. All right, pi over 4 is 0. That means we're going to go through the origin. And we can also set up kind of like an asymptote. Let me get a line here. I'm going to make it red and dotted. And pi over 4 will go through right here. And that is kind of like an asymptote. We're not going to cross it with our graph. All right, I'm going to go to black ink. Pi over 3 is negative 1.5. So here's pi 3. Negative is going to send me across the origin, 1.5 right here. Now this black point also has all the symmetry. I'm going to go straight across the y-axis. Here's a point. Back to the original, I'm going to go over the x-axis. Here's another point. And back to the original, I'm going to go across the origin. Here's another point. And let me put in at 3 pi over 4, we would also have a 0. So there's kind of an asymptote running through that part of the graph too. There we go. All right. Last one is the pi over 2 and negative 3. So let me go back to red dots. Pi over 2 is up here. Negative 3 sends me across the origin. So there's this point. And the only symmetry would be the origin or x-axis. That's going to send me up and put my final point right here. Okay, we've got the diagonals here, the pi over 4 sort of asymptotes. We can draw our 4 flower petals. I'm at the origin. I'm going to come out and do this one in the first and fourth quadrants. And then from the origin, I'll go up and do the flower petal in quadrants 1 and 2. And then to the left, we have a flower petal in quadrants 2 and 3. And then finally down here below, quadrants 3 and 4, flower petal. So there's our 4-petaled rose. Again, symmetry was a huge aid. We only needed these 5 points to get all those necessary dots to make that graph. So there's our example. Here is a checkpoint, a practice problem for you. When we look at this, it's cos of 3 theta. So this is going to be a 3-petaled flower. If you want to pause the video here and give it a try on your own, that's fine. If you want to watch through the symmetry test, that's fine. Again, just use the video to just get you through this example. And I'm going to write over here, symmetry. Let's see what we got. I'm going to check polar axis symmetry. We're going to replace theta with negative theta. And once again, this is a cos function. So it's 3 cos of 3 times negative theta would be negative 3 theta. And again, cosine is hungry. It eats negative, so that negative is gone. And we're back to our original function. So we have polar axis symmetry. Now we're going to check the line pi over 2. So we're going to take our 3 cos of 3 theta, and we're going to replace that theta with pi minus theta. Boom. Distribute the 3 cos of 3 pi minus 3 theta. Now remember, a trip around the circle is 2 pi radians. In our example, it was even. We had a 2 in there. So in this case, 3 pi would send us around the circle once, and then another pi would take us across. So right here, this 3 pi blows up our symmetry. We do not have pi over 2 symmetry. And now finally, pole symmetry or origin symmetry. This is where we replace the theta with pi plus theta. And some people figured this out real quick in class. Distribute the 3. We've got another 3 pi there. And that 3 pi means we're not going to finish where we started. We would not make it all the way back around the circle twice. So pole symmetry is also gone. So when we graph these, we're only going to have x-axis or polar axis symmetry. Okay, let's see what we got here. Okay, when a 0 goes in, a 3 comes out. Pi over 12 gives us 2.1. Pi over 6, we get a 0 out of there. Pi over 4 is negative 2.1. Pi over 3 has a negative 3 output. The 5 pi over 12 is also a negative 2.1. And pi over 2, we're back to 0. So here are our values. Let me see if I can do this. Copy. Whoa. Paste. Oh, dang it. I'll just read it off my paper. So yeah, here we go. At 0, we go out 3 units. 1, 2, 3. We only have x-axis symmetry, so that point is reflected to itself. We'll get no other points out of it. At pi over 12, that would be here, halfway between 0 and pi 6. We're going out 2.1. So 1, 2, and then just a little bit more. Now this point does have the x-axis to jump across, so we're going to wind up right down here. Okay, at pi 6, we had 0, so we come back and we hit the origin, and that means pi 6 is going to be kind of like an asymptote. I'm going to put this through here. There we go. Up next, pi over 4 was negative 2.2. Well, pi over 4 would be right in between pi 6 and pi 3. We're going to go across the origin. Negative 1, negative 2, and then 0.1 will put us right about there. Pi over 3, we had negative 3, so we're going to go across the origin. 1, 2, 3. And then 5 pi over 12 was negative 2.1. 5 pi over 12 is just under a half pi, so right here, we're going to go across the origin, negative 2.1 right here. Now, these 3 points are all below the x-axis, so all 3 of these are going to reflect over. So let's do this one out here first. That's on the 4 pi over 3 ray. So when we reflect, it'll wind up on the pi over 3 ray right here. This point is going to reflect up over the x-axis. It's going to wind up right here, straight up from where it was. And then finally, this one here is going to reflect straight up and be right here. So there we did predict this should be a 3-petaled rose, and there's our 3 petals. From the origin we come out, there's our first petal. Down here is another petal, and then finally up this way. If we had checked 5 pi over 6, that would have also been a 0 value, so there's kind of another asymptote. And think back when we did the symmetry, we said this did not have origin symmetry, but it does. You know, if I rotate it this way 120 degrees, this petal will land on this one will land on this one. If I go another 120, it will also land. So these symmetry tests, the 3 symmetry tests that we do, it's not a definite yes or no. A yes is a yes, but a no is more inconclusive. The symmetry can still be there even if we did not detect it with our test. And in class today, that's where we kind of ran out of gas. That was where we ended today's lesson. We do have one more example to do, example 6, and we'll tackle that one in class tomorrow, and I'll have to make another video for that one.